Hello, and welcome to the Modern Analytics Academy. My name is Chris Mitchell, and I'm a Cloud Solution Architect in Microsoft's Global Partner Solutions team, and I'll be taking you through today's session on data acquisition and storage. Our agenda today, I wanted to spend a little bit of time up front talking about what is the Modern Analytics Academy, the team that's delivering it. We'll spend some time looking at the various forms of acquiring analytical data, some decision criteria you might use to pick the appropriate one for your business case, and then jump into a demo of some of these technologies in action. So this is the team that's going to be delivering the Modern Analytics Academy. The Modern Analytics Academy was built to show you the breadth and depth of what you can achieve inside of Azure to achieve a modern analytics solution. Our presenters are all Cloud Solution Architects in our Global Partner Solutions team, and we're covering a variety of sessions in this academy. So today's session in data acquisition and storage, we're going to be looking at the various ways that you can acquire data using technologies like Azure Storage, Cosmos DB, messaging architectures like Event Hubs, and how that data lands and is accessible to your solution. In the modeling session, we'll be spending time looking at the various ways that you can structure and store your data, how you can explore and consume that data, and ultimately how you can model that data for downstream querying in the processes. In pipelines, we'll look at the ways that you can move your data through an evolution from acquiring the raw storage and transforming and formatting that data in a way that supports downstream querying capabilities. In security and governance, we're going to spend a lot of time looking at the ways that you can put security on your data, access controls, making sure only the right people get to see that data, and then how you can govern the data for using features like applying policy to that data, looking at data lineage, and making sure that you don't have data exposure by sharing sensitive information. And then ultimately with the visualization area, we'll be spending time looking at how you can use tools like Power BI to garner better value out of your this data that you've acquired and modeled by making it consumable by business users. So as I mentioned already, today's session is focused on data acquisition and storage. So for those who may not have attended our overview session, I wanted to take a moment looking at what a modern analytics solution may look like once it's realized in Azure. And so we've used this diagram as a canonical example that illustrates some of the core problems that you solve and address within a modern analytics solution. When we look at ingestion, we're looking at being able to connect to the data no matter where it comes from. In a modern analytics solution, you might find that data is coming from a combination of both on-premises and the cloud, social networks, maybe IoT sensor data. And you need to be able to acquire that data no matter where it's coming from and no matter what cadence it's coming at. In storage, we certainly want to look at how do we provide a highly scalable and cost-effective storage for these solutions. Data lakes make it possible to store theoretically limitless amounts of data, and it makes it more, in a modern analytics architecture, it makes it more about what data you decide to keep than what data you decide to throw away. But that doesn't change the fact that we need to be able to provide that storage, and that storage needs to be able to take advantage of modern security encryption technologies and be able to scale with the demands of your business. When we look at data exploration, this is all about using data processing engines and services for ad hoc exploration of the data and being able to make that data queryable. Prep and train is more about using those technologies that you may have used to explore the data, but more about taking that data and transforming it using data processing engines that may be able to do things like convert the data to more normalized data types, do lookups, apply machine learning models, etc., and other analyses against that data and prepare it for a format that is required by your business users for downstream consumption. And then model and serve, is all about access. Without giving end users access to the data and giving them the ability to do reporting and ad hoc analysis against that data, it's really useless. And so we have to service the data in a way that is usable and discoverable by your users via modern tools. And then down here along the bottom, this metadata management and governance, really, this is all about how do we make sure that even though we're acquiring all this data and we're making it visible and discoverable, how do we do that in a way that is still secure and trusted and compliant for your enterprise? So in our conversation today, we're going to be focusing on this ingest piece. And the ingest piece is very much about how do we acquire data from these systems. So we'll be talking about different ways to acquire source data and what's the process for ingesting that into Azure. And while I may dabble into the Explorer area a little bit, I'm really only going to be using Explorer as a way to illustrate the concepts that we've addressed in the ingest phase. So with that, we already talked a little bit about the fact that data is coming to us in a variety of different ways, right? Line of business systems, IoT data that could be an event stream. We could be connecting to APIs and social networks, transactional databases, files, and the like. And what we really want to look here is, these sources of data really fall into kind of a handful of patterns. And what we're looking at here is, what are the nuances of some of these patterns? So when we look at file storage, file storage is probably the most well understood form of storage we could look at, and so we probably don't need to spend a ton of time here. But there are a few variants of file-oriented storage that are available in the cloud. The one we're primarily going to be working with and looking at is Azure Blob Storage. While Azure Storage does offer you other modalities like queue storage and table storage and the like, the one that we see used most often in an analytical scenario is this file storage. And what this is really just file-oriented storage that's in the cloud. Database storage is another one you see a lot and you're probably very familiar with, right? It's a pretty well understood topic as well, but I think it's important to call out that what we're talking about here specifically is transactional databases. There's several different forms of transactional databases that are available as managed services in Azure, and picking one of those database platforms over the other oftentimes is more of a preference of your development team, or maybe the preference of a line of business application that you're using, than it is about version or feature support. For example, the capabilities that you're going to get for high availability, disaster recovery, backup, scalability, and the like are fairly consistent across Azure SQL, Azure MySQL, Azure PostgreSQL, and MariaDB. And these are all just various flavors of our database platform. So again, all these really fall under this umbrella. The important point here is that this is a transactional database that's offered to you in the cloud as a data source. Event storage is really quite a bit different than the modalities we talked about already, right? We're looking at, instead of a transactional database, what we're looking at is more of a message-oriented technology. So think about a gigantic message buffer that can handle a very high volume of real-time messages. These come up a lot in Internet of Things architectures and real-time analytics architectures, but effectively what they are is just a high-throughput buffer for event data. Often used for decoupled architectures, but the point here is that instead of writing transactions to a database, you're sending a stream of messages to some sort of an event queue. Examples of this in Azure include things like Azure Event Hubs, Azure Storage Queues, which I mentioned previously, Azure Service Bus, Azure IoT Hub even has this capability as well. So lots of different ways that you can offer some sort of eventing architecture, but really the key point here is it's a high throughput buffer for messages. And then the last one here to look at that's interesting is NoSQL databases. NoSQL databases oftentimes might be referred to as document databases. In fact, the Azure technology Cosmos DB was originally called Document DB. And the reason that's important is many modern applications are dealing with, prefer to deal with NoSQL databases over a traditional transactional database because of the benefits it gives it for dealing with JSON data, which is what a lot of applications emit these days, and being able to deal with things like flexible schema and the fact that, what defines your JSON document could evolve over time. And so it gives you some benefits over traditional databases in the fact that it's less, it breaks some of the classic challenges with a transactional database like schema rigidity and the like. So with this background, let's dig a little bit deeper into these different variants and look at each one, what each one does, and why and where it might be used in a modern analytics architecture. Okay, so Blob Storage, we talked about this a little bit already, but as we mentioned, Blob Storage is effectively just cloud-backed file storage. Some things that are interesting about Blob Storage, or I should say most of the features in Azure in general, is they're designed to be cloud accessible, and they're designed to be resilient, and they're designed to be scalable. So when you provision a Blob Storage account, you don't necessarily have to think up front about how much data you're going to put in that storage account. Unlike the old days of a SAN, if you set up a file share in the SAN, you might have to do things like think about how many disks that you're backing the SAN with, and how big it might get over time, etc. All that stuff kind of comes along for the ride with the cloud storage in Azure. You don't really have to think about those things. An important thing to think about, though, when you're using file-oriented storage is that all of your I/O operations are at the file level. All security is defined at the file or the folder level. So that means that if you have needs to secure individual rows of data that are within a file, this is not going to be provided to you by that file storage area. We do have a couple different mechanisms that we can offer you for security in Blob Storage. You can do authentication via Azure Active Directory, or we also have a more primitive version of security. When I say more primitive, less dependencies, it's defined based on secure access tokens. So you can do things like define secure access token policies and assign a policy that gives you specific access, either read access, write access, or read-write access to a file, and with an expiration date. So you can not only grant access, you can grant access for a specific time period. We support a number of protocols. Obviously, there's RESTful-based access via HTTPS, and then also a very common protocol used in analytics architecture called HDFS, which stands for Hadoop File System. There is a web-based HDFS protocol that Azure Blob Storage supports as well, so that if you're leveraging technologies that know how to talk to Hadoop, they should be able to talk to Azure Blob Storage as well. And a key thing that I think is really important here is that because all this is file-based access, the only rule that's really enforced on this data when it's stored is that it's a file, right? That means that anything could be in that file. It could be an image, it could be a CSV file, it could be a JSON document, anything. And so therefore, it's really important to keep in mind that Blob Storage, there is absolutely zero schema enforcement on any of the data that you put there. That is a very common problem that we face in analytical solutions, is what technologies do and don't enforce schema, and when you consume the data, can you rely on the schema of the data that you're reading? And we'll look into that. We'll look at that in later sessions. When we look at database storage, I think it's important to call out that unlike file storage, where you're really just sharing files, database storage is more, about storing rows of data transactionally. This is important because, not only can we say the individual row write is transactional, we can also do things like multi-phase transactions across multiple tables and multiple operations in the database. So you can say things like, I want to update this one row, insert these 5 rows, and delete that sixth row, and make that all as a single part of a transaction so they can succeed or fail together. So these multi-step operations operating as part of a transaction is a really important concept, right? That databases are exceptionally good at, that lighter weight protocols like dealing with files don't handle that very well. also gives you the ability to do more granular level of security. Not only do users have or not have access to the database, when they get access to the database, you can control what they have access to do. Do they only have read access? Do they only have read access to a specific set of tables, or do they only have read access to a specific rows in a specific table? All of those things can be done within a transactional database that you do not get with file storage. Now, this doesn't come without cost, right? So there's some additional things that come along with this, right? For example, connectivity to the database is done via specific protocols. So typically there's a driver in play. I mentioned tabular data stream here simply because I know about it. It's the protocol that SQL Server uses. Each database provider is going to have a different set of drivers you need to install and different protocols and a different syntax that you potentially communicate with it with. Now, most of them are going to be fairly close as far as, PL SQL, T SQL, ANSI SQL, but the point is that there is a driver involved for connecting to these source systems and the specific protocols that are in play. And another key piece that's in play here is that databases will do strict schema enforcement. That means when you're inserting rows into a table, it's not going to let you insert character data into a numeric column, right? It's going to also be able to give you the ability to apply rules like this column is required. This column has a length of 250 characters, so you can't put 251 characters in it. It's also going to do things like give you the ability to say things like unique constraints on columns. So you might say that this column has to have a unique value in it for a key, and so it will prevent you from doing inserts of duplicate keys and the like. There is even the notion in most relational databases for things like foreign keys. So you can say, hey, I'm not allowed to insert a row in this table unless the value I put in this column also exists in this other table, and that's how you do some rigid enforcement of schema and the like, and make sure that your data has referential integrity. So all these things are extra capabilities that come along with the database, but then also cause extra cost, and that extra cost, I should say, is largely experienced in what I'll say is performance. You can always write files into the cloud faster than you can write transactional rows to the database, just simply because of the overhead of examining and applying the schema at runtime. So super powerful, but also really designed for specific scenarios. Oftentimes we're going to see this come in play with line of business applications and things like that need to have a really robust transactional support. Event storage. I mentioned this previously. Event storage is really a real-time, high throughput buffer for sending messages. So some things to think about when you're defining event storage. Event storage is almost always temporary, right? You don't create a bottomless sink of messages. Typically what you'll do is you'll pump messages into a queue, and then you'll set a retention policy for how long those messages need to stay in there. So let's say we'll hold on to messages for a day or 7 days or something like that. All operations happen at the message level, and the security that's applied is at the queue level. So you can't secure individual messages, you only can secure the queues. But when you secure the queues, you can give different degrees of permissions to those queues. So you might say, hey, with this key, I only have read permissions to this queue, or I only have write permissions to this queue. And so that's the way that you could potentially separate the security, so the people that are writing only have the ability to write messages, not read, and the people that are reading only have the ability to read, not write. Those are all capabilities that you can do with the security. Support a variety of protocols that are often come up in IoT conversations. Obviously, the low-hanging fruit here that we always try to support is some sort of a RESTful-based API. That's what we talk about when we say HTTPS. But a couple other protocols we support. AMQP is a common one used. Kafka is another one. Some other things to look at here. Just like files, there's no schema enforcement here. When you send a message, the message can be a blob of anything you want, up to a certain size, and that's it, right? So certainly what is doing the writing, you need to make sure that what's doing the writing is writing that data in a consistent way, so that when you catch it on the other side, you know what you're reading. And then another interesting little wrinkle here is that while this isn't designed for long-term persistence, which I mentioned before, it's only going to hold on to the data for, that data buffer for a certain number of days that we've defined, it does have the ability to do something that we call Event Hub capture. And Event Hub capture is kind of neat because you can use it as a really easy way to take the messages that are showing up and then turn them into file storage. So what we'll often find is that you'll set up the event queue, you'll have something tap into the event queue so you can do real-time analytics on it, but then you'll also want to capture that same storage for long-term persistence. So that's a handy little feature there. And then the last one to look at here is NoSQL Storage. So NoSQL Storage, which we would look at primarily in Cosmos DB, this is pretty interesting in that many modern applications are using some sort of a NoSQL-backed storage, especially mobile applications and the like. What we'll find, there's some unique principles about NoSQL Storage that I think are interesting to call out. Specifically, this tunable transaction consistency is an interesting one. So you can dial the consistency model for an individual collection in a NoSQL database up or down, depending upon your requirements. And this is interesting because when we keep replicas of your transaction behind the scenes, that's our mechanism for resiliency and scale, and you can basically define how many replicas need to be written before the data is readable. And so that creates a lot of really interesting ways to both control the performance, but also control the transactional consistency of the database. Which is something that's unique and not done in other database platforms. Cosmos DB is designed for massive scale. We would call it a global scale database. You can make replicas of your collections all over the world. You can actually even have collections that have multi-master capabilities so that you can be writing to the same collection in multiple geographies, which is also really important as well. So if you're designing the next online retailer that's going to scale up to the likes of Walmart and Amazon and so forth, you could use Cosmos as a DB to back that because of the ridiculous scale that it supports. All operations really happen at the document level. And I think this is maybe a little bit of a misnomer in the fact that we have the ability to do multi-document transactions within the same collection. But primarily your operations, what I'm really getting at here, that your operations happen at the document level, is that you don't do an update statement on a single attribute of a single document. When you update the entire document. So if you have a 1 megabyte document and you're updating one field on that document, it's reading and writing the whole 1 megabyte document. So that's something that's slightly different than a transactional database. And the other thing to keep in mind here is that everything, the kind of the unit of storage behind the scenes is at the document. And that document, as we mentioned before, has a flexible schema. So that means over time, if you decide to add attributes to your documents, add additional fields to your JSON or rename fields in your JSON, all of that can be done because it does not do any rigid schema enforcement beyond a couple of things. Every document is going to have a consistent set of base attributes that it puts in there for things like, tag and timestamp and so forth that you don't provide. Cosmos DB is going to inject those behind the scenes for you. And then we also have this notion of a partition column. So when you create a collection in Cosmos DB, you can scale that collection. And the way that collection scales and it partitions and spreads out horizontally to give you good performance is by a partition ID. So if you define a partition collection in Cosmos DB, one of the things that you have to do is give it a partition ID. That is typically one of the columns in your document. Something else that's interesting about Cosmos DB is that we support multiple API protocols. Our first one was what we called the Document DB protocol, which is a SQL variant. So you can use SQL queries to query your documents. You could say select star from collection name, which would be your table name, where column date equals January 1st, 2021, and it would process that query just like you would, but return you a payload of JSON documents. We also support other common NoSQL protocols. Some of these are mentioned here. MongoDB is a really common one. Cassandra graph. Graph is a little bit unique in the fact that while it's storing JSON documents underneath the covers, the graph architecture is more of a different style of query. So you're looking at nodes and vertices, vertices and lines between those nodes. So you can do things like say, get me all of the, the people that are n number of degrees of separation from another person. And then table storage. So table storage is a primitive that is in Azure, Blob Storage. But one of the things that we've done here is we've taken the ability to take that Azure Blob Storage or the table storage API, but then service that up of Cosmos DB, so you can get Azure table storage with better performance and scale than the table storage that comes with Azure Blob Storage. And so this was largely provided for migration scenarios, but is also something that's another protocol we support. And then the last thing I wanted to call out here that I think is particularly interesting is that the analytics storage, all of this can be persisted via this technology we have called Synapse Link. So what is Synapse Link? So we say Synapse Link here for Cosmos DB. Synapse Link is something that's going to be coming to a variety of other technologies as well. One of the ones to call out as an example is the Dynamics Dataverse. So if you have Dynamics and you're using the Dataverse inside of Dynamics, we also support Synapse Link for that. But what's happening behind the scenes is when you write records into your transactional data store, which is Cosmos DB, behind the scenes we're automatically synchronizing that content that lands into that transactional data store over to an analytical store that is columnar compressed using Parquet behind the scenes. And then we give you the ability to query that data directly from the Spark endpoint in in Synapse. Why is this important? Well, one of the common challenges that you're going to deal with in a messaging architecture is, or some sort of a transactional architecture, I should say, is when messages arrive, those messages could be inserts or updates or deletes. And how do you make sure that your analytical store stays up to date with not only the inserts that occur, but how does it also stay up to date with the updates and deletes that occur? Earlier when we talked about using Event Hub, it's a lot easier to deal with a data stream that is append only than a data stream that is handling not only inserts, but is also dealing with updates and deletes. And because of this is a super powerful tool because it takes all the mystery out of keeping that transactionally consistent analytical store behind the scenes. There are other ways to implement this type of architecture. We'll talk later on in the model and serve sessions about how you can use technologies like Delta to achieve the same end goal, but that's a very code-intensive approach for this. And Synapse Link is designed to be, for lack of a better term, an easy button for addressing this style of problem. And so what we have enabled here is the ability for you to very quickly enable that analytical store on top of data that you're landing inside of Cosmos DB with a number of options that you can tune. You could do things like tune to sync the deletions, but you might also have a Cosmos DB store that has a time to live on your documents, and you might want to say that, hey, don't synchronize the documents that are getting deleted via time to live. So you can make this a very deep long-term store for all the data that flies through transactionally in your Cosmos DB environment. It's a super, super powerful tool that's really, really, really easy to implement, and we'll show you that a little bit later. So I've shown you a whole bunch of different technologies that could potentially be leveraged as the data that backs your analytical solution. But I think it's important to look at some of the criteria that you might use to determine which is the appropriate one to select based on your needs. Sometimes you might not have the luxury of making a selection. Sometimes the selection may be dictated to you, right? If you've already got an existing system that's feeding you files, chances are you're not going to be able to, easily change that to a messaging architecture. If somebody is already providing you a transactional database behind the scenes and they've given you a view to connect to consume the data from it, you're probably not going to be able to, force an architectural change there. But assuming you have the ability to jump in and make recommendations or suggestions on what the appropriate architecture to use is, here's some of the things that you might want to look at. So the first thing I would think about is, what is the data I/O pattern, right? Is the data coming to me in, waves, meaning batches? Do I get a notification every, once a day of here's all the new data, once an hour or so forth? Or is this something that's coming to me real time, right? Real time would drive me more to like an eventing architecture. Is the data read-write? Is the data write only, append only, or is the data also, do I have to account for things like updates? Am I expecting the data that I've already loaded to change over time? What are the security needs that you have? Do I need to have rigid, robust role-based security? Do I need to have Azure Active Directory, or can I use some sort of token-based access? Is that allowed? And then the final one here that speaks to some of the other things we've talked about already, but is still important to call out as a criteria is, what kind of latency can I tolerate? Obviously, if you're getting something that is, daily batches, there's kind of an implied degree of latency that exists there already. But for nearer real-time architectures, is the latency that I'm allowed to account for, is it measured in seconds? Is it measured in minutes, hours, days, so forth? That might be a factor that kind of pushes you towards why you might leverage Cosmos DB with Synapse Link versus using something like Azure Event Hubs plus some other technologies to real-time stream the data into your analytical store. And the technology that I'm talking about there is a technology that we'll cover in later sessions called Azure Stream Analytics. But there are ways to use that high throughput memory buffer or a high throughput event buffer that is a event hub to really quickly capture those events as they land in the hub and then stream them into the database and make them queryable real time. And so that would be something that you might leverage as a decision criteria to choose Cosmos DB with Synapse Link versus Event Hubs. So here's another thing to look at that I kind of, instead of talking about what the factors you want to consider are, where do each one of these technologies really slot into these, I/O patterns versus, transactional support, etc. So what we're looking at here is this general comparison of the aspects of each of the different styles of storage we've talked about, and most importantly, how the decision criteria might impact your selection of each one of these things. So for example, storage, we called out previously that this is a really classic example of a batch architecture. At some regular cadence, you're going to receive one or more files. You process those files downstream. Someone might argue that, if each file represented only one row of data, wouldn't this no longer be a batch solution? Wouldn't it be more like a messaging-oriented solution? While that's technically true, the pattern really is more akin to messaging, and in the real world, I don't think you'd ever want to implement it that way because of the inherent performance burden you'd take to come along with that. So regarding the transactional nature of this, the transaction boundary, if you will, is the reading or the writing of an individual file. So the file write succeeds or fails all by itself. If there's a need to deal with potentially I write a series of 5 files together, while that may be a business problem, you have a business transaction that's not supported by the file system. So you would have to do something to coordinate the writing of those 5 files in sequence and make sure they all succeed together and roll back the write if it didn't. And the important thing to consider is even if you try to build some business process to support that, it doesn't mean that downstream systems might not have been able to read that file for a period of time while it existed. So really important to keep in mind that the transactional nature of this is once the file is completely written out there, it's available for query, and there's not really anything you can do to control that, and there's not anything you can do to extend that transactional boundary across multiple files. For database storage, records are written. They can be written in singleton fashion if you want. They can also be written batch oriented if you want. There's no reason why you can't say I'm going to insert 1 million records into this table and write those all in a single transaction. And so databases are often used for batch oriented solutions. But what's nice about a transactional database solution over File storage is, the things that we talked about. The fact that you do have some schema rigidity, so you can make sure that when I write the data, I'm writing data that is appropriately formatted for downstream. And you can also do, multi-phase transactions, right? You have this ability to, write and read across multiple tables and have all that succeed or fail together. However, it is also important to consider that, in order to use a database architecture, there are going to be some limits to the volume of data that you store, right? And, more often than not, when you look at a relational database in one of these modern analytics architectures, it's usually something that exists because of an upstream system that you don't have control over, right? There's a line of business application that is needing to do some sort of a multi-phase transactional system, and that's where your your data is coming from. Or you need the ability to do that in your architecture. You need the ability to kind of control the collection of rows that succeed or fail together. I mean, you need a pretty rigid control over that. Event systems, they really shine. We talked about when you're dealing with a really high volume and low latency, right? These systems are designed to deal with arbitrarily large volumes of data. We talk about like millions of events per second, right? Those are the types of things that you can do in an event-oriented architecture. And no transaction support here at all, right? You effectively write an event, it's a fire and forget it type of thing. So that's important to keep in mind. Most often, I think these shine really when you're talking about some sort of an append-only environment, right? You take a queue and you just feed a series of messages, and those messages all stand on their own. They could maybe be an update to some downstream event, but really each event is kind of independent of all other events. So think of that kind of like an append-only table, if you will. And then NoSQL Storage, we talked about this a little bit. It's got this interesting mix of the benefits of a database without the drawbacks of a database. The schema enforcement isn't rigid, but you still get some transactional capability. But it's almost kind of message-oriented in the grand scheme of things. And one of the reasons we look at it as being kind of message-oriented in the grand scheme of things is that there is this ability to process data off of the change feed in NoSQL Storage, almost like it's a message bus. In fact, the programming semantics behind it are nearly identical to how you would read messages off of an event queue. And most importantly, because of that Synapse link feature that keeps that synchronized analytical store in play, that is another way that looks like a more of a real-time messaging architecture. And so you can kind of use a NoSQL solution as this kind of intermediate happy medium between a transactional database and event storage. And so that's kind of what we're trying to convey here in this. Alrighty, so what I'm about to do now is jump into a demo that illustrates a handful of these concepts. Before I jump in there, I thought it would be useful to show you a little diagram of what I built here. I'll just help bring it home. So, first of all, I have a little lightweight thing in .NET that's going to generate a series of events. And the series of events it's going to do are not really important for the purposes of our demo, but just to give you an idea, it's designed to be kind of like an IoT scenario. So it's generating an event per second for a number of devices, and these devices represent a collection of sensors that are going to have a temperature, humidity, and I think pounds per square inch of pressure. I just kind of did a random number generator that's got a few elements on each payload. And so what it'll do when it sends this event is it'll send a timestamp, it'll send a device ID that the reading is for, and then those 3 values for those readings. And we're going to send that data to both an Event Hub and the Synapse link. And so once I've done that, I'm going to turn on Event Hub this feature of Event Hub Capture. Event Hub Capture will take those events and it will start writing them out in a series of files out to the data lake. And so you'll see what that looks like. And then once we've got all this running, we'll be able to go into Synapse and start showing you what it looks like to query these files. For example, what does it look like to query files that are persisted out of the data lake? What does it look like to use the Synapse link and query the data that comes out of Synapse link? And then finally, we'll also turn on Azure Stream Analytics to capture those events that come out of the Event Hub and real-time write them into a table. And then we'll query that table out of Synapse Link as well. And what we're really going to be showing here is the fact that there's more than one way to solve the problem, but it'll give us a great opportunity to look at, what are the various, latency considerations that come into play with each one of these technologies, and that'll help you think about why I might choose one versus the other, since they're fairly similar in their approach and design. So without further ado, let's go ahead and jump into the demo. All right, so taking a look at the demos, the first thing I wanted to show you was a simple console app that I have running in VisualStudio.net. So this application is pretty straightforward. What we do is we create a collection of IoT devices and then iterate through those on a regular schedule, generating some new events for those devices, and then sending those events to both Cosmos DB and Azure Event Hubs. And just to show you here, I've got the console app running, and you can see the types of events that it's generating. You can see for a device ID, temperature, RPM, and PSI for these devices, and we're doing that, on a fairly good cadence. So let's go over into the Azure portal and take a look at what's going on. So the first thing that I wanted to look at was Cosmos DB. So remember, with Cosmos DB, we're sending JSON documents, and we can go into the Data Explorer for Cosmos DB. You can see that we've created a collection called events, and we can navigate down into the items and see those individual items. As I mentioned, we're going to be using the Azure Synapse Link feature. And just to show you what that would look like, if I created a new container, I have an option down here to turn on the analytical store. And basically what this means when I turn on the analytical store is it says, for this collection, synchronize those events over into that analytical query store that's available to Synapse. The next thing I wanted to look at here is the Event Hubs. So if I go over into Azure Event Hubs, you can see that I've got the Event Hub here, and you can see I've got a series of events that are going to it. I've got some charts. And if I drill down into the individual Event Hub, you can see that I've got an Event Hub called Events. And I've turned on this Capture Events feature. So the Capture Events feature gives me the ability to determine if it's going to save the events that hit the Event Hub into Azure Storage. And I have some things that I can configure that define, how frequently it generates new files. The minimum you can go here is 1 minute. So basically what would happen is it would buffer events, and then every 1 minute it would spit out the events that are in the buffer into Blob Storage. I could define the storage account that those events go to. And then I can also set up some things about the storage path that it creates. And you can see here I've taken mostly the defaults. It'll put a folder for the namespace of the Event Hub, the name of the Event Hub. If there's a partition, it'll create a folder per each partition. In this particular case, we're only using a single partition. And then it'll build this year, month, day, hour, minute, second structure that is really common in the way we store data in data lakes at times. And so what it's going to do is, behind the scenes, as we feed events into the Event Hub, it's going to automatically be creating those files and filling up that event location, or that storage location. So let's go over and look at how we would consume a couple of these things. So the first thing I want to look at here is the workspace. We're in the Data Hub here, and you can see we've got some attached Blob Storage, and we also have an attached Cosmos DB. So we've linked both of these things to our environment. And so the first thing you can see here is under Blob Storage, if I go into Events, I can look at that folder structure, and I can see, the folder structure for the first partition, year, month, day, hour, and drill down to those individual files. And you can see behind the scenes, it's creating a .avro file. So avro is a pretty specialized storage format. And so that's an important thing to consider here. That avro format, we have zero control over how it writes that data. All we know is that it creates those avro files and pumps the body of the messages into those files. That's something that's important to consider. If we go over to Cosmos DB, you can see that it's just showing us that we have the collection here. But what's nice about Cosmos DB is I can get some really great integrated behavior. So I can right-click here and say select top 100 rows, and it's automatically going to build the query for me, sets up the connection in the appropriate way, and uses this open row set capability. I've already got a couple queries here written that show me how to do this. One of these scripts here. I'll just go ahead and use this one. If I click run here, you can see what it's going to do is it's going to select the top 100 rows that are in that have been replicated over via Synapse Link. And after I do this, I'm also going to take the same query. And so you can see here it's returned me the rows. Because the data structure that's in JSON is very flat, it was able to figure out to just promote all those attributes that are at the top level of that JSON document to columns in this result set. If I'd had a nested structure, it's only going to deal with the top level of that nesting. So if I had an attribute that had additional sub-JSON elements in it, like arrays and things like that, that would show up as a JSON payload, and I might have to do some supplemental processing on that. And so just to give you an idea of the latency, if I did a select count star on this, this is going to just count the rows that are out there. And then it's going to give me an idea of how far behind the event stream I am. And so you can see I've processed 1,300 rows in Synapse Link, and we're at about 1,500 here. So I'm a couple hundred events behind. The other thing I think you'll notice is that when you run this 1,300 is going to be the result value for a little while, because what's going on behind the scenes is it's not processing these into the data lake real time. It's picking them up in batches and updating the Parquet structure. So the latency behind the distance that you're going to be behind the events as they're written into Cosmos DB is going to vary over time based on how frequently it's doing that processing. The general guidance we have is it can be up to a 5-minute delay before that data is visible to your lake, visible to Synapse in your data lake. So that's something to keep in mind. Now let's go over and look at how we deal with the events that are showing up in Event Hub Capture. We showed you that we have these files out here that we can work with, but since they're in an Avro format, there's nothing inside of Synapse that lets me query it directly like I had with the Synapse Link data. So I need to actually go in and create a work with a notebook that I've created. And so I'm using some things in Databricks here, and in Databricks I have the ability to do the spark.read and tell it that the format is Avro. And I point it at that location, and then it gives me the ability to start querying and working with that data. So I'm going to go ahead and kick this off. It's going to take a little bit for the Spark session to get started. And so we'll take a look at what those results are once the Spark session gets started and look and see how far we are behind on the data set. Okay, so now that the Spark session is started, we can go ahead and do things like get a count on our data frame. And this will tell us how many rows that we've processed. You can see here 2,509 rows. And if we look over here, we're at about 2,700 rows. So we're a couple hundred events behind. And again, this is a factor of the fact that we're only generating a new Avro file every minute. And so our data that we're querying here is always going to be up to a minute behind. Another point to consider is that we've got to write code in order to process this data. It's not as integrated as the Cosmos DB. And so there's some additional things you'll have to consider. Like here, you can see that the body of this data is embedded within a byte array. And so there's probably some things that you're going to have to do to process this data and make it queryable. And you'll also have to consider how you, do this on some sort of a scheduled cadence to make it available. The final thing that I wanted to look at was using a feature called Azure Stream Analytics. So we're using the Event Hub again, but instead of using the Event Hub Capture, what we want to do is we want to tap into the stream directly. So I have this thing running that's called an Azure Stream Analytics job. We're going to go into this technology in more detail in later sessions, but the important thing to point out here is that I've been able to define an input connection that points at my Event Hub, and this is just pointing to that Event Hub that we're sending the events to that you can see here. I'm also able to point at an output location. This output location is actually pointing at a table that is in a provisioned SQL pool inside of Azure Synapse. And then the final thing is we've written a query. And so the query is how we map what's coming from the input into the output. So we select the specific columns we care about from the events into the output destination, and this output destination happens to be a table called events that is in Azure Synapse. And so if I pop back over to my Synapse portal here, I have a query that I'm doing a count star on this events table again, and if I run this, you'll see that 3,276 and I'm 3,300. So you can see I was only about 25 events behind there. And really the ability to see the answer here is a function of how quickly I can switch windows. So you can see we're very close to being up to date on this event stream. And the reason for that is we're picking up the events and we're writing to that destination database real time. And so this is a way that if ultra low latency is important to you, Azure Stream Analytics is a very, very great way to deal with the volume of events coming into that event hub and process them and send them on in the ultimate low latency. So to recap what we just looked at in that demo, because we covered a lot of territory, we started off with a little .NET console app that sole purpose was to generate some fictitious telemetry events. That console app sent those telemetry events to two places for us, both to Event Hub and to Cosmos DB. In Cosmos DB, we turned on Synapse Link, and we leveraged the easy integrated features with Synapse Link to query those documents from Synapse by being able to just right-click on the collection in Synapse and generate new SQL queries. We also turned on the Event Hub capture feature in Synapse and in Event Hubs and looked at the different features that it enables us to do there, like specify the structure where it lands the files. With that capture feature, we were able to look at how it generates Avro files, and we used the Synapse Spark pools to write some PySpark code to leverage Spark data frames to read those Avro files and look at some nuances of how that data is processed. And then finally, we generated an Azure Synapse Analytics job, and we use that Azure Synapse Analytics job to process the events out of Event Hub in real time, writing them directly to an Azure Synapse table in a provisioned SQL pool. Now, each one of these things gives us the ability to process those events, but each one of them has, some different nuances when it comes to latency and simplicity and ease of use. And we just wanted to call those out because while all three of these mechanisms may be a way to solve your business problems, it's important to think about the trade-offs that you choose as far as latency and simplicity goes. And we wanted to make you aware of all those nuances. So with that is the balance of what we wanted to cover today. We just want to remind you that if you go out to aka.ms/MAA, you'll find some resources regarding the Modern Analytics Academy. And out here you'll find some information about the various sessions. We'll be posting session recordings out here, slide decks, and we'll also be including hands-on labs in the future. So if you want to dig deeper on any of these topics, you can do so. We thank you for joining us today, and we look forward to seeing you on a future session.